Hi, chemistry students. Hey, let's talk about reaction rates here in Unit 9. And I'm just going to go through here our slideshow. Now, with reaction rates, you can think of a chemical reaction that maybe starts with a couple of reactants, and as soon as one of the reactants is used up, then that reaction is done. Whereas in some cases, you could have reversible reactions. So this is kind of what's shown here. Oftentimes here, this is shown as two gases reacting, but yet there can be this back and forth, forward direction, backward direction, reverse direction, and it can reach an equilibrium. So there's that. In all of this, we're thinking about the way reactions occur and what affects those reactions. And so sometimes it's beneficial to use graphing for that. So you're going to see some reference to graphing. Now, activation energy. So if we look at this graph here, we see an E value, E sub A. That is the activation energy in both of these cases. And both of these are chemical reactions, but they're a little bit different in that the one on the left here is absorbing energy and ending up with a product with a higher energy level than the reactants, whereas on the right we have the opposite, where the products have a lower. So in this case, energy is absorbed, and in exothermic, energy is emitted or lost. More about that. So the whole thing is known as an activated complex, where bonds are broken and reformed. And so here's a list of some of the factors that enter into the rates of chemical reactions. And for example, like the number of reacting species, that would be the particles that we're reacting, has a role in that, in the sense that the more there are, the better the reaction rate. The physical state of the reactants could be either gas, solid, or liquid, and so that's what's represented here with the G as a gas. Here's S for solid, and then sometimes you'll see an AQ, which means that is aqueous solution, which means a solution that has a concentration with water. Complexity plays a role in reaction rates in the sense that if there's more bonds to break, then it's going to take longer. So fairly simple inorganic compounds tend to react pretty fast because there's fewer bonds that break and reform. Whereas with organic compounds, where there's a lot of carbon, you tend to have a slower reaction because there's a lot of bonds that'll be breaking and reforming. So complexity has a role. Concentration is all about, the higher concentration, the higher the rate. So that's pretty much common sense. Gases, react pretty fast because they have access to all the atoms have access to each other. And then pressure can play a role. So if you think of the higher pressure, that's going to increase the reaction rate. Surface area. Surface area plays a role because the smaller the particle, if you have a large chunky particle, the things that are wanting to react with it aren't going to come in contact as easily as if you broke it up. So if you break up into smaller particles, then the reactants that are trying to react with it would have more access. So smaller the particle, the higher the reaction rate. Here's another diagram showing that. So as you look through these, just kind of keep these in mind. A lot of it is common sense. Now there's some terms here. Homogeneous means that they're just the same state. Like two reactants that are gases are homogeneous. Whereas if you had different physical states, then you would have heterogeneous, like say a solid and a liquid. Okay, temperature. Temperature is all about kinetic energy. So if you raise the temperature of something, of the reactants, then basically you're increasing the kinetic energy. That's going to increase the reaction rate. Okay, catalyst. We saw catalysts in biology, but catalysts tend to decrease the activation energy, so that's their role, and they're used often. There's also an inhibitor. You can add things to chemical reactions to slow it down. Okay, I hope this helps, and good luck. Thank you for watching.